Good afternoon. Let's make start. It's given me great pleasure to welcome with Mr. Willem Toet here to give us a lecture on engineering design of Formula One car. Willem is an old friend. He, at various stages of his career, was head of Aero at Benetton. Willem, please correct me. Ferrari and BMW, Sauber. And on the different title, he took overall responsibility at Honda, right? Honda Racing and so on. And in between, he was once he was a managing director of Ray Malik Limited, a sports car company making what is that rally car tour.
Touring cars and Le Mans cars.
So that was around 2011. And when he was in charge, the company won 5 championships. But somehow he loves engineering and went back to design cars.
So while we're thinking about RML, is my microphone on? I think it is. Yeah. So at RML, we won 5 championships, and the company had a reasonable turnover. And one of the things you must do when you run a company is you must make a profit. If you make a loss, eventually you are out of business, and actually quite quickly you run out of business. So at RML, we won 5 championships, and I had to then be very creative, shall we say, with the value of the second-hand cars that we had at the end of our racing season in order to make any profit at all. So the boss, who's a good friend, so the boss and I sat down together and we agreed, perhaps my priorities are not really with making money, which is what he wants from the owner of the company. You can imagine, the owner of the company needs to make money. Me as an engineer, I want to win championships.
Are you trying to say something to our EVPP? Come back to teaching and research, because that's what he loves. Okay. But anyway, let me continue. So,
if you make a loss, you become a university.
William is a good friend and a tremendous supporter for university research. He loves students, and I would say he's one of the most generous Formula One designers I've ever known. And he works with universities around Europe, with students, with his knowledge, money, even on different projects such as Formula students and so on. I remember, I don't know which year, he came to Southampton, worked with 4 of my students to design a world record-breaking Formula One car to run on Bonneville, right? Salt Lake. Okay, that was a true inspiration to our engineering students. So what else? I have lots of story, but I will stop here and leave the floor to Willem Toet. Okay.
Don't need that. Welcome, everyone. So you'll see very quickly I have no enthusiasm for life whatsoever. None left. Used it all up. Not. I'm very relaxed when I give a talk. You'll see that as well. I'm very enthusiastic about my subject matter. If you have a burning question, you can't wait any longer, stick your hand up and maybe I'll answer the question. Now, I have to be careful because I can't give away all secrets, but I do try and give away as many secrets as I can. So, I wanted to start just to tell you a little bit what the talk will be about. I'm going to mention just very briefly the structure and also the level of education used in Formula One. Talk briefly about Formula One regulations, some of the challenges that you face maybe when designing a car. I'll use one example. And sometimes business and racing or engineering needs clash. So I've already given you one example. You need to make a profit if you run a company. Mercedes, who won the championship this year, by the way, last year made a loss, but anyway, they're covered. Mercedes will cover it. So some different lessons that I've learned in the past, and then the contribution of aerodynamics. And people often ask, at what speed does aerodynamics make a difference? I'll talk about that a little bit. And how much lap time do you make from aerodynamics in Formula One? And then just a few very, very quick insights into aerodynamics in Formula One. I wanted to just briefly, we're at a university. Now, I wanted to show you some of the trends that I see changing in Formula One. And one trend that causes a difference is the size of the team that you're in. So we get a breakdown of things related to administration, human resources, finance, marketing, Marketing, I think, is the hardest. As an engineer, I think marketing, finding the money, is the hardest thing in Formula One. Because I can't find the money. I'm an engineer. I can spend it really effectively. Maybe even efficiently, I can spend it. But it's hard to find it, but it's vital. Also, you can imagine. And then creating the thing that we're racing, you have to do, and then designing and improving. And a table of numbers like that to me means absolutely nothing. But let's ignore that table and look at this table. So using my many years in Formula One, and in particular, some teams that I know well, talking to a few people there, a small team will tend to have a higher proportion of older people because a small team needs experienced people. A bigger team or a team that's growing will tend to bring in more younger people, and they will tend to come in with an ever higher level of education. So the numbers I've used here is the number of years on average that from the information that I've been able to gather, in each type of role, the average number of years a person has spent in high school plus university. Now, again, it's just a table of numbers, so it doesn't mean very much. Now, last time I cover this, so let's go back to it for a second. Because of the smaller teams having a higher proportion of older people, people who got into the game because of experience more than because of, if you like, training, then their education level is lower. And as the teams get bigger, they tend to have a higher proportion of younger people, and they're coming in with more education. Now, there is sort of a downside to the high level of education, and that is specialization. When I started in Formula One, I actually started as a model maker. I had a degree, but I wanted to get into Formula One. I had a job as a model maker. I wanted my toe inside that door. I got my toe in by doing a job as a model maker. And it was really useful. I joined an aerodynamics group of one person and made it 2 people. By joining an aerodynamic, by having an aero group of only 2 people back in the 1980s, you had to do everything. Design the parts, make the parts, test the parts. You go to the wind tunnel and the software used to run the wind tunnel isn't very good, so you write your own software. You want to understand where to spend your energy, make the car faster, so you write software to simulate a lap going around a racetrack, things like this. The people coming in now are more highly educated. On average, I would say more intelligent. We're attracting people with high levels of IQ, but they come in and need to specialize. So as a group leader, I will move people around, first my group, and then encourage them to work in other departments in the company. If I want to be selfish and want to keep the power to myself, the best thing is not to let your people grow too much, but that's not me. And so to train, let's say, the future technical directors of a company, you need to move your good people around. And to me, the other really interesting thing about the difference between a small and a large Formula One team, if you just look at the numbers of people in, let's call it administration plus finding the money, make it happen, and design an improvement, well, they're all increasing, so it doesn't really tell you much. But if you look at the proportion of people, you don't need so many people. You don't need as the same percentage of people to create your vehicle when you have a big team as you do when you have a small team. When you have a small team, you need a big percentage of that group actually just making the product. And if you have to cut down, the one area you can cut down is research and development. Big teams, of course, have the bigger research and development teams. Now, Formula One cars are very nice toys. Very high drag coefficient. Good road car, we were just talking about road cars, a good road car, drag coefficient, 0.22 today, BMW 5 Series. I've been doing some work recently for Audi. Their, let's say, equivalent car, the A4, A5 Series car, has a drag coefficient of a little bit under, but the nearest number is 0.23. So they are upset. And one of the things that is changing in the world of road car manufacturing in Europe is that the guys who used to have the power, the individual geniuses who will design a car through style, are being, if you like, replaced by more engineers who have to do the hard work of making the car. You still have to keep the car with the in-house style, but you need to make the car more aerodynamically efficient. So money is being spent, a lot of money is being spent on engines to make the engines more efficient, but also on aerodynamics to reduce the drag. Now, a Formula One car will have a drag coefficient of something like 0.8, 0.85. So compared to a road car, it is complete rubbish, but we'll see why that is later on. It's fundamentally because the downforce makes more difference than the drag. Now, 0 to 100 kilometers an hour, 2.6 seconds, it's okay, but if you ask a racing driver, it's nothing special. What's special about a Formula One car is the 200 to 0, especially 200 to 150, takes almost no time whatsoever. And then being able to corner at more than 4G of cornering. If you want to set out to design a racing car, a Formula One car, or for that matter, any type of vehicle, you need to start with the regulations. And in Formula One, it's a slightly special sport because the regulations are spread around a number of different documents. So you have your technical regulations, you have an appendix to the technical regulations, you have your sporting regulations, what you can do at the racetrack, what you can't do at the racetrack, but also sporting regulations include a limitation on how much research you can do in aerodynamics. You have technical directives. These are an explanation by the rule makers. This rule, we've been asked a question, and this rule, this is how we will interpret it. You have, as well as having a public, let's say, it's not made public to the public, but it's made public to all the teams, as well as having an explanation of how the rules will be interpreted to the teams, you will have an individual team writing and asking a question. If I'm a poor team and I can't afford to do something, and I see that a rich team is spending a lot of money in one area, I might write to the rule makers using a language that says, we wish to circumvent the regulations by doing this, and stage 1 will be a small step forward, but we think stage 2, stage 3, stage 4 would be. And so one of the things we might do is write to them saying that we want to use passive aerodynamic devices to switch the flow on our aerodynamics, and we're going to switch every surface on the car using this trick, and it's going to lead to a complete upheaval and so on. So you might write in those terms to try and have something banned, or you might say, we want to try something, we think the gain will not be very big, but we'd like to see if we can gain a small advantage doing this, and you don't explain everything, but you hope that you can. So, in my past, this was nobody ever laid out and said, this is how it is. You just got the rules documents. And I felt that was not really fair, so I started to create for myself, first, a spreadsheet of all the explanations you got from the rule makers, both private to the team and in general. You would lay out what regulation it applied to, a summary of the material involved, so that if this was your area, you could find it. And then I created a complete single document. This is part of the document I had at Sauber when I was there last. A complete single document that lays out, in particular, my aim was for the aerodynamics people, that lays out what the rules are and how this team will interpret the various rules with little pictures and explanations and diagrams and things. And in some Formula One teams, so if any of you end up in a job in Formula One, and it may seem remote, but actually you have certain advantages here, but that's by the by. If you end up in a job in Formula One, then I would expect you to see a document a bit like this. If there isn't one, you need to be knocking on the boss's door to say, hey, I need to know what the rules are so I can do my job properly. Some technical directors in the past would hide that information and keep it for themselves so that they kept the power. This is not a sensible way for a team to work. What the bigger teams, so for example, what Mercedes have done is Mercedes have 2 or 3 people, each one of which could be the technical director, and they throw them all in and they tell them, boys, you will work together. You will find a way of working together. So that means, number one, no single genius can hold you to ransom because you've got 3 or 4 of them all working together. So you eliminate the risk of being held to ransom. And then you end up with stopping the other teams pinching those people because you pay them enough that you can afford. You pay them enough. And so generally speaking, engineers will not earn big salaries. But in Formula One, the salaries are in the multi-millions for the people at the very top, the engineering people at the very top. Now, it's in Formula One, unlike most other sports, it is the words, the letter of the law. If you can find a clever interpretation that circumvents the intent of the regulation, you get away with it. You can. In other formulae, it's much, much more difficult. I'll give you one example. I've played in the past using exhaust systems to create an aerodynamic effect. Now, it can be quite dangerous. So in the very distant past, we used the exhaust underneath the car, in the diffuser of the car, to create downforce. When the driver is on the gas pedal, and the driver's on the throttle, then you get extra rear downforce that helps you go around the corner faster. It always used to worry me. With a driver like Michael Schumacher, he could handle it. With a driver like Eddie Irvine, who was his partner at Ferrari when we were both there, then Eddie would have much more problems handling a car that would change balance depending upon exhaust position. And so if you imagine giving the car gas, you get more grip, but the driver gets too enthusiastic, gives it too much gas, the tail starts to go off in a corner, so he comes off the throttle because the tail's going around, and then he'll spin it all together because he's lost downforce. You have to be careful. What's happened in the last, say, 10 years is the mechanical engineers in the companies have found ways to understand better the mechanical systems that will allow you to balance a car if it becomes unbalanced from an aerodynamic perspective. So that's made it possible to play with systems that are maybe a little bit aerodynamically unstable. Fly-by-wire systems are still effectively banned in Formula One. We're not even allowed traction control. So the team started to play with having an exhaust pipe jetting the air directly beside the rear tyre, which turned out people have tried different places. So we've tried underneath, over the top, to the side. To the side was always the best, but it was, for example, if you blow on your suspension, you risk damaging, you risk breaking your suspension through heat. You also risk things like with metal wishbones. When we tried it in the 1990s. You risk the car changing wheelbase or rear steer because you're expanding and contracting the track rods, things like this. But a few years later, so 2009, 10, people started to experiment with putting the exhaust pipe in different places. One was near the front of the floor to try and create a vortex near the front of the floor, but the way that worked best was beside the rear tyre. But for 2012, 10 and 11, they allowed teams to race. In 12, they decided, let's ban it. All the teams have got it now. Let's go back to having the exhaust doing nothing. So they said, okay, your exhaust pipes have to point uphill at the back. So they have to point backwards, but uphill at least 10 degrees. And then just to make sure we didn't play any games, they said behind the exhaust must be a 3-degree cone where you're not allowed, expanding cone where you're not allowed to have any bodywork. But of course, the starting diameter was the same. You ended up with an exhaust pipe a little bit like that, and even in deeper channels, where the exhaust pipe points up at 10 degrees, but at an angle 3 degrees less than the exhaust pipe, you start with a nice little curve, and air very nicely follows a curve, if I can find a piece of paper. No piece. Air will follow a curved surface. I'll draw. Air will follow a surface, and we ended up with the exhaust pipe, the exhaust gas, right down directly beside the floor of the car, next to the tyre. Now, I'm going to mention a lesson I learned at that time while I'm here. At Sauber, from the day BMW withdrew from the Sauber BMW team, which was the end of 2009, Sauber started losing money. With a budget of something like 100 million US dollars, roughly, Sauber were losing approximately 10% of their turnover, so 10 million US dollars a year, and it was obvious that that could not continue. So I rejoined Sauber in 2011, and part of my job became to earn money. In my department, I had to break my department up a little bit. My department started to earn as a profit for the company. In 2012, we earned 15 million profit from a department of about 100 people. I had to take roughly half my people, not do Formula One, do paying work. So in 2012, with half my department doing paying work instead of Formula One, I was very aware that we needed to be careful with the use of our resources. So when we were developing this Coanda exhaust system, this aerodynamic trickery exhaust system, when we were developing it, we very quickly realized that the design of the overall car with exhaust system, and let's call it without exhaust or without Coanda exhaust, we had a diverging path of evolution of the shape of the car. And from lessons I'd learned in the past, I realized if we used half of our department to do a Coanda exhaust car and half of our department a non-Coanda, each one would be developing at something less than the full rate. Probably not half, because your evolution tends to flatten out after a while. So we fought hard to focus entirely on the Coanda exhaust design, and that car was the best car Sauber had in the last years. We'd scored 44 points both seasons before. We scored over 120 points in that season. It was only one place in the championship, but it meant a lot of podiums, a lot of publicity. Really important lesson for us to learn. Towards the end, I'll mention briefly innovation. That also plays a part in developing a new product, and a very important part. But in the end, as the boss of a group, I cannot tell my geniuses, you guys, I can't tell you what new ideas you're going to invent. You have to invent them yourself. So as a boss of a group, I can't demand just innovation. That doesn't work. I need to think of the number of human resources combined with the financial resources that I apply to a problem, and that will tell me what expected development rate I will have. Now, the rules of a car you see in the shape of the car. The bottom image gives you, this is an old set of rules, but what year doesn't really matter. And so you start, as a designer, you will start by creating the regulation boxes. I gave this talk a month or so. I gave this talk in Italy, and I've still got an Italian bit of text on the top there. That says some rules from 2009. And sometimes just doing a simple plan view sketch, read the regulations and do some simple sketches in 2D to understand where the rules are. And so one of the rules we're looking at there, oh, I've got a laser. One of the rules, this pinkish area here, this is an exclusion zone where you're allowed to have a suspension, you're allowed to put your TV cameras because they don't have to comply with the same regulations. You're allowed to have your brake ducts, but you're not allowed to have bodywork in any of that pinkish area. This actually is a plan view of a simplified 2017 Formula One car where the rules do change. And actually, this piece of bodywork encroaches into, right there, encroaches into the rules box. So sometimes a simple thing like that can help you to find a potential problem with regulations. Once you have your regulations box, you need to then lay out the parts of your racing car. The things you have to have. You have to have your powertrain. You'll already have some sort of a model of what your powertrain looks like. You'll need your driver, your suspension, your tyres, your fuel tank. You need to lay these things out in a simplified way. Formula One is a regulation that limits the weight distribution, so you need to make sure that the masses are distributed sensibly. Get on to aerodynamic regulation. If you have a set of regulations, so thinking still about Formula One, where you are evolving smoothly from one year to another and the rules are not changed very much, then you would expect to have a reasonable idea of where you will start your next season and perhaps even where you will finish your next season from an aerodynamic perspective. And the same will apply to the structures guys, the powertrain people. All these estimates of where you will be in the future are put into a model, simulated, and then each department will be given information about what the other department's performance will mean. So let's assume the powertrain people say, we're going to find 100 horsepower more. If they find 100 horsepower more, the aerodynamics people will be told in turn, powertrain people have found more power, you can afford more drag, therefore you should be looking for more downforce and not worry so much about the drag. In 2014, the story was a little bit different. You go from 150 kilograms of fuel in 2013 to 100 kilograms of fuel in 2014. Therefore, you need to be thinking more about your drag. And for 2009 in particular, we had some issues with our ability to predict the future. But let's say your ability to predict the future are not very good. Let's say I believe that my downforce level will be lower than it turns out to be in the end. If this is the case, the structural people will have got the instruction, we've got new regulations, we think we're going to have less downforce. So they will think, great, we can save weight. And therefore, we can add more ballast in the car and put the centre of gravity lower. So if this happens, and then you tend to find as you're doing your development, well, actually, no, we found ways around the regulations, we're going to find the downforce back, then the structural guys will have to scramble and put more strength in the car so it doesn't break. So I expect that at a university you're going to learn a great deal of the science behind designing vehicles, a great deal of the science. What I think is also important to learn is getting different parts of a company to talk to one another so that you end up taking advantage of the limits of every part of a set of regulations or every part of the performance of the car. So having a regular discussion and re-establishing your targets is part of what needs to be done. In the rules for 14, we went from wide wings to slightly narrower. For 9, 10, 11, 12, 13, we had wings as wide as the car. We used to often lose front wings in the first corner, so they said, okay, let's make it a little bit narrower. Then for 14, we also went from high noses, which had a limit. The limit, basically, the high nose used to be, it's about 50 mil lower than the rim of the cockpit, so you could never have a nose going over a cockpit in a normal accident. But the rule makers were worried that some of the accidents we'd had were when a car is following another closely, you're following another car, the car in front brakes much earlier than the car behind believes is going to happen. And as a result, there is a sudden change of relative velocity one to the other, and the car behind hits, at the last minute he swings out and he hits the rear wheel with his nose. That will send the rear car flying. Flying accidents are the worst sort of accidents in Formula One because you have no idea where the flying vehicle is going to go next. But to avoid flying accidents, the rules were changed to have low noses, and a lot of experimental work was done to prove that that worked. Then exhausts were finally put in the middle. They have, instead of having a cone behind, they have a stepped difference in diameter. So now it really is difficult to make the exhaust work. You also have a minimum diameter of exhaust pipe that is so big that the exhaust velocities are lower, so it's harder to do something with the exhaust. You can still play with the exhaust, it just has less effect. Standard side impacts, low nose. The lower rear wing was eliminated from the regulations. The upper rear wing got a smaller box where we have to fit it in, and so on. And then also you had the different powertrain. Now the new powertrain, we used to have V8, normally aspirated engines, 2.4 litres. They had a rev limit of 18,000 revs. If we didn't have a rev limit when they introduced the limit, the highest RPM was 20,000 RPM. But the rev limit was introduced in order to reduce the rate of development. The engines were frozen for a number of years in terms of design. And we went from having what for us, aerodynamically speaking, was a very simple vehicle to having a vehicle with a V6, 1.6 litre, turbo with a big turbo. The turbocharger would have an engine, an electrical engine attached to it, which you could use to both drive the turbo, but also use as a way of using the heat from the turbocharger to generate electricity. So they were much more complex vehicles to create, and in particular, the control electronics needed cooling. In Formula One, all cooling must be done with the velocity of the car. So the items we had needed cooling, but the cooling had to be achieved passively. We went from about 10 electrical boxes in 2013 to 35 units that needed cooling in 2014. So a lot more work to do. Two of those units that needed cooling, by the way, were the cables from the battery pack to the motor. They have two electrical motors, one attached to the internal combustion engine, one attached to the turbo. And the unit attached to the internal combustion engine, the cables were too small, so we needed to cool them. And electrical insulation, you probably realize, is also reasonably effective thermal insulation, so we needed to blow a hurricane over these things. It was a bit silly. Then energy recovery usage increased, intercoolers were added, and these systems really did have an impact on the weight of the car and the design complexity of the car. If you look at the overall size of the radiator, the intercooler is a big chunk. In parallel with all of this, long discussions were happening. Sauber were a poor team. Long discussions were happening with our engine partner, Ferrari, about the cost of engines. So we went from paying roughly $6 to $8 million US per year for the engines plus the gearboxes that we got from Ferrari, to being told that we would have to pay $30 million a year. So Sauber were already losing money at $10 million a year, and then Ferrari came along and said, by the way, the cost is going from 6 to 8 million to about 30 million a year. So the boss had no choice but to get hard and argue about the money. Now, so because 14, we all knew it was going to be a big change in regulations, we were given some initial information in 2012, and then started work with a few engineers on the design of the new car. Typically a Formula One team, if the rules don't change, you won't start designing work on your new car until the old car has done its first race. When the old car in March has done its first race, then you'll put a lot of people onto the new, but you also continue to develop the old. So that means you actually have rather less than a year to develop a completely different car from scratch. And that's something the Formula One teams have got very good at, very experienced at. They understand how to take that design cycle and shrink it to, say, a 6-month period. But with completely new regulations, you do always need more time. Now, we begged for more updates, but in the meantime, the bosses are negotiating hard about the price. Now, at one stage, what the boss did was said, look, there was no movement from Ferrari, and actually, in the end, there was no movement from Ferrari on the price. That's what you have to pay. So the bosses said, well, we're going to talk to Mercedes. Well, you can just imagine the big bosses of Ferrari. If they're going to talk to Mercedes, well, there's no way we're going to give them any secret information because we've definitely got the best engine. They were convinced. Yeah. All the manufacturers were convinced we had the best engine. Because so Formula One engines today, I don't know if any of you know the thermal efficiency of engines, but a good diesel-powered car is going to be something of the order of 45% of the energy in the fuel ends up on the ground. Formula One engines are more efficient than that. And because they're petrol engines, nobody had a petrol engine that was producing better than 45% thermal efficiency, taking 45% of the energy in the fuel and putting it all on the ground. So all the manufacturers thought they had the best. Well, actually, it was Mercedes that ended up with the best. Anyway, in the meantime, the boss was negotiating hard, and one of the negotiating tactics was, we're going to go to Mercedes. So the engineers, in the meantime, we're begging for information. We're wanting information. And as soon as this happened in about late in 2012, so I had a meeting in 2012 with Peter Sauber and Monisha Kaltenborn are the bosses of the company, because I'd been hammering them saying 2014 will be a disaster. They said, Willem, you've been complaining about not having enough resources from the beginning. In 2012, you produced a car that was on the podium half a dozen times. It can't be that bad. So they organised a meeting with the people who work directly under me. Now, this, if you're a boss, is always a bit of an issue. When the bosses call a meeting with your people, because you need to, and we had very little notice, so my people are called in. So Willem said to us that 2014 is going to be a disaster. But he's exaggerating, right? It's not going to be that bad, is it? You know, they think they're trying to put words into people's mouth. Most of my people, what will people do when they're put under pressure by the bosses? They tend to say nothing. If the big boss says, it'll be all right, won't it? Well, people will say nothing, won't they? Yeah? Happily, one of my boys, an Argentinian man, was brave enough to stand up and say, no, Willem's wrong. He's definitely wrong. It won't be a disaster. No. It'll be a massacre. So thank goodness. But anyway, it made no difference. The truth is, at Sauber, there was no money. We could not. So I was told, look, we know you're earning all this money. We'll be able to spend a proportion of it instead of... So we hired out the wind tunnel, got a lot of money for that. We did various things. So they said, look, we'll be able to do some more CFD. Could we do more CFD? No. We had to hire out our CFD resources as well. Now, it doesn't help to be right when a disaster is coming. Yeah? So I've now left Sauber. I was fired, by the way. I've been fired from some very good jobs, but this one, I don't mind leaving this one because Sauber are still financially in trouble. They have new owners. The new owners have paid off a massive debt, and now they've come to realise, oh my God, we still have 40 people aerodynamics, and we're fighting people with 200 people doing aerodynamics. I don't know. Now, Sauber will have a fighting chance to score some points. So in 14, Sauber did have a disaster. It was the first year they scored 0 points. In 15, at the beginning of the season, they scored some points because you look at what other teams are doing, you use every bit of resource you've got in your head, and you try and scramble forward as much as you can. But when you can't even afford to put parts on the wind tunnel model, you know it's not going to be good. And for 14, for me, 14 was a really interesting year. When regulations don't change very much, I like to look at numbers. I find numbers really interesting. Human beings are more interesting than numbers, but even numbers are interesting. In an average year, you don't get very much change in the championship positions. If there's nothing causing a change, things will tend to go on changing, if you like, gradually. So an average of 0.8 championship positions per team, 1. Then you get to a change of regulations and you get a bigger change. And here you'll find the rich teams are still the rich teams. But what's the big mover here? The big mover here is Williams. Now they had 2 changes. The biggest thing that they did was Claire Williams, the boss's daughter, took over control of the company, used this and said to Daddy, Daddy, we need to invest. We've got a new set of regulations. You saw what happened in 2009 with the previous big change of regulations. We need to invest in 2014. This is our opportunity to put more research in. So they did. And they went from a Cosworth engine to the Mercedes engine. So they threw the balls in the air. They picked what they felt would be the best. They chose correctly. Claire Williams, again, chose correctly. Did a really good job. And Williams actually held their position as well in 15. And Sauber took a big drop because 0 points, scored a few points again. And it was McLaren that have gone backwards because they, afterwards, they chose a new engine supplier. And for me, I've got nothing against Honda, but I think any new engine supplier coming in, they have been shocked at the level of performance of the new powertrains. Because most people just don't believe that 45 to 50% is now normal. Recovery of energy within the fuel. Now, 2009 was a previous set of regulations where I learned a lot of lessons. BMW bosses said, okay, energy recovery is coming in for the first time. We want energy recovery on the car. I argued against it, saying that I felt it would be not the right thing to do. And they could not understand, and I completely failed to convince them, that it would be wise to throw away a potential, and it was only potential, but a potential quarter of a second a lap. So the energy recovery systems used then worked on the rear wheels. We had a maximum of 80 horsepower we could then use from the braking energy we recovered, or 80 horsepower for 6 seconds. But if you use it all on one straight, you have the ability to overtake, so that's a strategic advantage, the ability to overtake, and a quarter of a second a lap. So why would I argue that? Well, the energy recovery system came with some disadvantages. I reasoned in advance that we would use between 30 and 40% of my department's resources just packaging it. So BMW decided that they would have air-cooled batteries because liquid cooling was too expensive. They were the only ones who went air-cooled. It's a disaster to go air. You need liquid cooling if you've got a lot of energy, if you're expending a lot of energy. So we had a battery pack that we mounted beside, the battery pack had to be within the crash structures. It had to be somewhere near the middle of the car to keep it protected. We had 4 batteries deep, and I can't remember what array, but in front view you also had a number of batteries on each side and a number of batteries up and down. We had to cool to the same temperature range, the front battery and the back battery with the same air. As an engineer, you think, that's not possible. So of course it's possible. So we ended up making a battery pack, investing a lot of in the end, cooling is the responsibility of the aerodynamics department. So you end up spending a lot of energy taking a drinking straw. So we started with literally drinking straws, Coca-Cola drinking straws. You take the air past the first 2 batteries, and then you let some of the straws are shorter to cool the next battery, and then some of the straws go all the way to the last battery to make sure the last battery also gets cooled. What a nightmare. And we ended up spending 40% of my whole department's energy on all sorts of things that are directly and indirectly related to packaging the energy recovery system. Now, when you have a set of regulations, the 2009 regulations were designed to halve the downforce. We knew that we would be very low on grip when we started the next season, so we knew that finding more downforce would be a very important thing. But to look at the cars, there's a 2009 car, there's the 2008 car. So the cars had much wider, this was the first year of the big wide fat front wings compared to narrow. Central section was a lifting section. All the appendages we had on the cars were banned. So from the side pods rearwards, you have to have a very generous radius on all bodywork, and any little wing or thing you stick out won't have a generous radius over it, and therefore, big change. I said, look, here's a normal plot of development. Doesn't matter where your starting point is. This is last year's car, say. You do development. Now, in my department, as my people, we can change which curve we follow by being more effective, by being better people at developing. You as a boss, all you can do is change this amount. And what you're doing is taking us back. We'll be slower. I said, okay, take the previous plot. There's my middle curve from the previous plot. Here's my new regulations. This is what happens. And I expect we use 40% of our regulations. We're going to miss out on 0.7 of a second. So that's how I tried to explain to my bosses that I'd be happy to give up a quarter of a second a lap because I would guarantee to find more. Of course, they didn't believe me. Now, so if you ever find yourself in a situation like this, you have to learn how to manage your bosses. I was never good at it. So I learned a lesson a long time ago. I used to shout at my people when I was really young because I thought they're useless. They just have no brains. And actually, it's true. I was a bad manager. I didn't give them space to learn. The truth is, once I had so many people, I was forced to give my people space to learn. I realized, actually, that kid's not bad. He's actually done a really good job. He's just gone about it a completely different way to what I would have. So I was a bad manager. But I've never been good at managing my bosses and never really learned. So that's a very important lesson to manage your bosses. Find a way to communicate that lets them understand that you're not trying to just get more resources or you're not trying to help yourself, you're trying to help the project. And here's my life history where I've actually remembered in my lifetime to file away numbers. So the numbers don't mean anything. I don't want to give anything away on numbers. This is from 1987 through to 2010. Every year where I've actually been able to go back through my filing cabinet and find numbers, I put numbers down. So you've got a change here in the regulations in the middle of 1994. And by the time you get to around here, the cars are aerodynamically less efficient than we had in 94, with just the rules keep changing to slow down the cars. But actually they operated over a much broader, for example, we didn't do yaw testing so much back in those days. We didn't do the extremes of attitude that you can do today. The cars of 2008, cars of 2008 were actually over the range of all attitudes that they run as efficient. And then 2009, we started with a complete disaster aerodynamically, but even using 40% of the department's resources to do energy recovery, we ended up going very, very quickly to a level of performance that was only about, the green car is a 2007, so they're only about a year behind. Other teams did an even bigger job and ended up the start of the season 2009 better than their previous cars. And what's changed? For me, I'll tell you what changed. When developing the new car, I had one experienced guy I put on to developing the new. You can imagine, as the manager of a department, if I'm head of aero, I throw in some of my own ideas, but I don't have time to do the aerodynamics anymore. If you're managing 100 people, you haven't got time to do the aerodynamics. Your people do the aerodynamics. I had one old guy and some young people, and all the good ideas actually came from the young people because the old boys, so if you're an old boy, you're developing aerodynamics on a formula car, one of the best strategies is just to say to every idea that comes along, that'll never work. And when you've been trying, so a Formula One team will be trying 2,000 ideas a week, every week, every year, yeah? The old boys, us old boys, we know, we've tried that before, it won't work. Yeah? We know, but we're wrong because your understanding reaches new levels. And through working with Professor Zhang at Southampton University, I started to really learn how a motorsport diffuser works. And the aerodynamics of modern Formula One cars is completely different. The rules change. You can't use a surface anymore to make something happen. You've got to use airflow to make it happen. And the young guys just had the better ideas. They didn't have that old, it'll never work, we've tried it all before. And 2009, actually, so you had a very similar 7 to 8.8 of a change average, and 2009 was a huge change in the way the teams performed. That was actually the first time that Red Bull, who'd been nowhere, took a step up. And Red Bull have a huge aerodynamics department and a great aerodynamic genius as well as a huge department. So they invested and took a step up. Braun with the Honda engine, so a cruel twist of fate. Braun invented something called a double diffuser. It's just a way of opening a slot in the bodywork that made the diffuser, that gave you a bigger diffuser, more expansion, where the rules basically forced you to a low level of expansion. So the idea behind the double diffuser came to Honda, and the Honda engineers, you can imagine how they felt, especially when Braun started doing well, that they've invented the double diffuser. That's one of the ideas that made the team win, and Honda even paid for the team to operate for a year rather than pay redundancy. They thought, we'll do the right thing, we'll pay the team for a year. So the Honda name is gone from the car, and yet they win the championship with a Honda idea. There's a couple of guys in Japan who just had this crazy idea, and they ran it past Ross Brawn, and Ross Brawn was smart enough to sell it to the FIA as just being a minor thing. We'd just like to clarify. Then afterwards, you get a bit of a resettling. So you had BMW Sauber had done quite well, and their last year they did bad. They did rather worse, and so. The teams I've now labelled in green for 2009 were the teams that ran with energy recovery systems. So all of them took a step back. They all bounced back a little bit, except BMW Sauber, because BMW Sauber had no money. It wasn't BMW anymore, had no more money. And this is a plot I got very recently from the guys at Honda. And 100% is where their 2009 car would be. And this is February 2008. So they were already, in February 2008, better than their 2008 car with new regulations. And that's because they'd understood the aerodynamics. So, simulation helps you to understand where to spend your research money. If you use engineering factors, tyres come out number one. You can't design the tyres. You have to select them from a list. You're not going to get that too wrong. The vehicle mass, they're all below minimum weight. They carry ballast. You're not going to change the vehicle mass. The power as a team, unless you're a Ferrari or a Mercedes or a Renault, all the other teams, they don't do the power unit. They only use it. They buy it and use it. So what's left is aerodynamics. It looks like it's low on the list, but this is my way of hiding what's really important. So here we have a plot of speed against distance around Barcelona. This is a simulation. Simulation is always correlated to reality on a regular basis. Many times per race is in Formula 1. So let's mathematically turn off the downforce. We go 21.46 seconds a lap slower. Now this we can't simulate. We don't simulate. But we can simulate changes in downforce level, and every time you put an update on the car, you'll check this. So these simulations are very, very good. But that's not fair. Sorry, before I say that's not fair, I said earlier, at what speed does aerodynamics work? Well, actually, very low speed. In a slow corner that is 70 kilometers an hour, that's not fast even in a road car, 70 kilometers an hour, you'll make 8% difference with aerodynamics with an average aero setup. 8% at 7. Now, this is a plot of speed against distance. Distance isn't lap time. If you did a plot of speed against time, the slow zones would all spread out and the high speed zones would all shrink. So you spend actually a long time in a slow corner where you gain 8%. So aerodynamics makes a difference to Formula 1 and to, say, Formula Student makes a difference at the lowest speed of the events that you do. It's not fair to just change the downforce. If you eliminated the downforce, most of the drag that the car carries, it carries because it is inducing drag through the downforce. And if you reduce that to, say, 1/4 of reality, you'll still have the cigar shape of the car, you will still have the tyres that are exposed. You recover, on an average circuit like Barcelona, only 2 seconds. So that's why the drag of a Formula 1 car is so high. The drag is important, but not that important. Now, how do we develop? 3 main methods: computers, computational fluid dynamics, wind tunnel, and gathering data on the track. The wind tunnels we have in Formula 1 are the best wind tunnel toys, wind tunnels that you can find. That's me in the middle of the Sauber wind tunnel in the BMW days. The BMW is gone now from the sign, but that's a big toy. The tunnel's capable. It has a 3 megawatt fan, 6 megawatts of cooling, capable of doing 85 meters a second. Stainless steel belt, you can run full-size cars in there. Good toy. This is a 60% model in the wind tunnel. Wheels on model. Wheels are made of rubber. Now in the BMW days, we used to do what we'd call a display model. We don't bother with the display model anymore, but in the wind tunnel, you can move the model up and down. You can pitch it. You can yaw it. You can steer the wheels. You can change the diameter of the tyres through pushing down on the rubber tyres with little motors. We can change the pressure in the tyres. We can blow exhaust. You have so many degrees of freedom with a wind tunnel model. All this happens under computer control dynamically during a wind tunnel run. We're limited on wind on time, so we ramp the wind up as fast, so we use the full 3 megawatts of power to ramp the wind up to speed. We use software trickery and a lifetime of experience to stabilize the wind and the wind temperature at the same time. So you have closed loop control during the wind-up, and within 30 seconds, not only you're on speed and on condition, and you're able to start work. And then you switch on so you start open loop, and then you switch on a closed loop control system to then maintain your conditions. But they are unbelievable toys. A pit stop to us is like a pit stop at the racetrack. The guys are ready with their next part. The aerodynamicists are ready with their data analysis. As soon as the run finishes, we take, let's call it, zero forces at the beginning and as a check at the end. As soon as the zero forces are taken, the aerodynamicist is in the control room doing his analysis as fast as we can, and we spend huge amounts of mental energy creating, if you like, ways to warn the aerodynamicists of a significant change from the previous baseline runs, but also to go through 512 pressure sensors, front wing balance, rear wing balance, overall balance, wheel balances, underfloor balances, all sorts of sensors, wind tunnel sensors. We go mine that data to look for any significant change. And quite often you'll have a change where the aerodynamic balances change, so just the front to rear balance. If you increase front on a typical Formula One car, if you increase percentage front, your efficiency will look good. But we know how the standard of car adjusts. So we can adjust for a change in aerodynamic balance, a change in drag, because we know how the car adjusts also for drag level, a change in radiator cooling, a change in brake cooling. They're all things we can make an allowance for so that we know when the run's finished, we know. And I didn't really talk about the computers, but we have supercomputers for software. They're not very super anymore because we're restricted on how much we can do, but huge energy has been spent on CFD software so that the software we used 5 years ago, the software we use today, is about 10 times as efficient. So it used to be we'd think to ourselves, we cannot afford to do full dynamic simulations. We have to do Reynolds average simulations. It's not necessarily the case anymore because the compute resources are so much more efficient, software-wise. Another thing that the Aero group will do is any fluids in the car we will look at, including the exhaust. So we've got this simulation. We got basically 1D information from Ferrari, then put the 1D information into our exhaust simulation and use this. This is a baseline run for before we did the co-under exhaust and then. I like this because this is a visualization. So part of what we've learned in Formula One is how to get a picture of the aerodynamic information in your head so that you can understand what's happening with the airflow. This is called a lambda 2 image. So lambda 2 is vorticity. So this is the speed of rotation of the air. We've taken surfaces of ISO, let's call it vorticity. Surfaces that show the same speed of rotation of the air. And the color is how much energy, what's the total pressure, how much energy remains in the air. But to simplify, and it took me a lifetime of working in the game to realise what I want to do with the air, apart from, I mean, it's obvious to say less drag, more downforce, that's obvious. But actually what I want to do with the air is the rules force with boxes, they force that the air coming either side of the driver's ears, let's say, either side of the driver at about the driver's eye level. There's nothing allowed in the rules. The driver has to see, so below driver's eye level, you're not allowed anything. That air coming towards the driver, what do I want to do with it? I now know that what I want to do with that air is I want to turn it, and I want to take that air and send it underneath the car. What we actually do with the wings, if you look at the front wing of a Formula One car, there are lots of winglets, lots of elements, but there are also lots of vertical elements that in themselves generate zero downforce, and they take energy out of the air, which means they create drag. But we are creating dozens of co-rotating vortices all of them are taking the air that's coming towards the driver, circulating it down and pushing it underneath the car. So you have clean, high-energy air acting on the front wing, and then you have clean, high-energy air going underneath the car as well. If I look at all the Formula student cars out there, nobody's got it yet. And there are 2 or 3 teams that I've told, so you're the next team that I've told, if you're in Formula SAE, there's some work that, now, Formula SAE cars are very short, so it's very challenging to do, but I'm convinced there's a win in Formula Student there for the first team that get their heads around it and understand how to achieve it, because that's the hard part. Now, I want to mention F ducts briefly. So anyone who follows Formula One will have heard of F ducts. They were invented by McLaren in 2010 after the double diffuser. Now, the double diffuser taught all teams that if you have a small jet of air in the wrong place, it'll cause a stall in the flow, and that's a disaster. Now, here is a cross-section through the centre line of the McLaren style of wing. I haven't got McLaren section, don't worry, they've not given me that secret. But this is the style of wing. So the air's coming from here. They used a very clever duct. It has to be a 2-element wing, but you're allowed some extra space in the middle. So in the middle, it wasn't a 2-element wing. So you've got a nice energising jet there, a nice energising jet there. And then they introduced the F duct, which would cause a stall in the flow. And if you look, it would also stall the second flap. It would cause a stall in the flow. Now, that's the bit that's the actual aerodynamic mechanism at the wing. That's the simple part. Very easy to imagine. If you're an aerodynamicist working on a wing, you introduce a jet at 90 degrees to the flow, it's going to have some impact. It doesn't take very much air to have a negative impact. The clever part, that's what it looked like. That's a photo of the wing. This is looking at the central energising duct in yellow and the F duct in green. And a number of people have tried to explain how this works. Now, if any of you use the working, let's say, website LinkedIn, LinkedIn is, let's say, like a Facebook, but for business people looking for a job mainly. In LinkedIn, if you look up my name on LinkedIn, I've got a number of posts, including one about double diffusers, including one about F ducts, where I explain much more than I can in the time I've got here. And the ducting to do this is actually quite difficult. If we go back to our picture here, the area of the wing where the F duct jet would come out and stall the flow is an area of low pressure. The F duct entry was on the nose. It was a scoop on the nose where you'll pick up high pressure. So you've got a duct going from high pressure to the rear, which is low pressure. What would stop it going there? Okay, on the way, it goes via the cockpit, but the cockpit is neutral pressure, let's say. So why would the air not permanently, even going from neutral pressure to low pressure, why would it not go there? A number of people have tried to explain this with the various diagrams, and they just haven't understood. There's nothing. Why would this air not flow here as well as here all the time? And the smart one, I think, was Craig Scarborough, who runs a Formula One blog and website, and he's a commentator on English TV as well. And he was a smart one. He waited until a few years later, and he bought this air box with an F duct, piece of ducting on it from Force India. Every team did their own invention on how. But one look at this. So this is the air coming from the cockpit front of car. And it is, let's call it the switching mechanism that changes the flow from the upper duct to the lower duct. You can see just from one image, you can just see from the shape, there's a lot going on there. And I think that's all you need to know to understand that to develop a system like this, actually, McLaren invented it. And I know the man's name, he hasn't given me permission to give his name, but I know the man who invented the F duct at McLaren. That took a lot of work. So it took someone to have the idea, this is how we're going to do it, but you needed engineers. So the actual idea, we want to create something that will stall the flow when the driver wants, was a great idea. They didn't even ask the rule makers, they just put the ducting in. The rule makers didn't see what it did. The driver just used to use his knee in McLaren, just put his knee against the duct and it would switch from one to the other. And the good thing is, and this is Red Bull's F-duct system. So you can see physically this is quite big. This is the rollover hoop, the main hoop behind the driver's head. This is the rear wing back here. And in between, you've got this massive set of ducting that actually doesn't do very much, but it does, every bit is vital. And they put what in English you would call a vanity panel. So if I'm sitting at a desk here, and I don't want you to see my legs, I'll put a vanity panel in. So that's what the English would call a vanity panel, and every desk in England would have a vanity panel in front. And so they put vanity panels on their F-duct so that no one could see what they were doing. But of course, every team would invent their own, so it didn't. As soon as you knew this was a top secret area, well, that's the area you need to focus on, isn't it? But we all had drawings. So here you've got a pressure of, let's say, plus 0.8. In there you've got, let's say, neutral, plus 1 there, and you've got minus 1.2 to maybe minus 0.6 there and there, the same. So the reason you had the switch was having the jets of air working at high speed to be able to switch the flow, and it was hard work. There's one other thing I want to mention. I have another love. I'm overdue, but I have another love, and that is innovation. Now, one of the reasons I have a love for innovation is I'm not a great innovator myself. I've learned, I've invented a few things in the past, but as I've got older, it's got harder and harder to invent new things because you've tried to think of everything already. And my bosses would always say to me, from the beginning of my time in Formula One, the bosses would always say, well, work smarter. You get all these acronyms that people pull out. Work, S-M-A-R-T. I can't even remember what it stands for, but work smarter, be more intelligent. So yeah, we've got less money and less people than everybody else, but we just need to be more intelligent than they are. So, okay. So how do you do that? Yeah? So you think that we're just smarter than the people at Ferrari, McLaren, Mercedes? So the bosses would always demand, and one of my bosses came up with a lovely phrase for the invention that they want. They would call it a bracket. So, a device that you use, a 90-degree device that you would use to bolt two parts together, a bracket. Billy Ramph, one of our bosses, said they want the 1 second bracket. You just want the bracket that you invent that bolts on the car, costs 0 to manufacture, 0 research time to develop, and just bolts on the car and makes it go 1 second a lap faster. That's a great idea. Can you design it for us, please, boss? Yeah? So the 1 second bracket doesn't really work. But innovation, real innovation, there are ways of stimulating innovation. So one way might be put yourself at the risk of death and you will find a way to survive. Now, I know that works for me, but it's very rare that you put yourself in a position of being at risk of death. And that's not a very smart thing to do as a boss. Now, for me, this little invention here, it's the horns on the front of the BMW car. You could think of it as an innovation because it was a new device we invented and put on the car. But how was it invented, and how were all these many devices on the car invented? Quite often, just someone has an idea. Now, this one was invented because I asked some very hard questions of my CFD group. And Tomo Sato, we called it a Tomcat because Tomo Sato is head of CFD at Sauber Motorsport and was when I was there as well. He invented it, but we asked him the question, why is there still energy in the airflow at the back of the car? Well, the answer is there's air coming past here and the rules don't allow you to put anything in the way. Well, can't we do something to change the airflow so we move that air to a place where we can do something with it? And all these devices along the car so these things roll up a vortex that moves high energy air to a place where you can do more work. So you can think of it as being an innovation, but you can also think of it being a logical process of coming from how can I do something with this air? And I would say there, I'm going to stop, ask for questions. So who's brave? Who's going to be first? No. Look at that. It's brave, but 2 questions. Yeah, you can ask 2 questions.
First, the engine size, and you had like a 1.6 liter on the internal combustion engine. It's required by rules, right? And how about the battery? Because remember, this is a hybrid engine. You can have do you have any constraints on battery, the weight?
No constraints on battery whatsoever. The teams develop with battery manufacturers. They develop their own so that we use unstable technologies, you know, because Williams had a fire where they allowed the battery to go outside its normal range of suitable charge.
But if the battery, you can have like more power if you have more battery there. The weight,
Okay,
yeah.
right, I apologise.
Yeah.
Yes, there are limits. We're only allowed to use 160 horsepower maximum.
Okay.
And
Yeah.
we are only allowed to use 4 megajoules of energy through one lap.
All right. Okay. Okay. Another question for the transmission. And is that automatic or manual? Or how many speeds you use? Because remember, this is for racing, not for the passenger car. You know.
Yes.
Yeah. All right.
Okay, so we are limited in Formula One to having no more than 8 speeds. So all teams have 8 speeds. And actually, in 2014, we were allowed 1 ratio change during the season, 1 new set of ratios during the season. Now that the cars have been racing for some seasons, you have 1 set of ratio, and you have to use those ratios for every event of the year, the same numbers, if you like, same reports or same ratio numbers, and each gearbox or each set of gears has to do 4 or 5 events, but 8 speeds. And so if you allow the teams freedom, wherever you allow the teams freedom, they will take advantage of it. If there's 1,000th of a second in a race, they'll do it. Even if it's, you know, if it's so small per lap that you can't measure it, if you can calculate that it's going to be, they will do it. And they just decided, look, if all teams have 8-speed gearboxes, no one will have an advantage anymore on the gearbox.
Forget about the regulation rules. Over the last 20 years, if you say, what have we learned from the aerodynamic viewpoint? Can you give me two examples?
Great question. So the question is, over the last 20 years, what have we learned from an aerodynamic perspective? So I've learned a lot about making a formula car faster. But what have we learned that's going to help road cars, passenger cars, the planet? Probably nothing, except we've learned how to make our CFD software more than, in the last 5 years, 10 times more efficient. We did another factor of 3 before then. So working on computational fluid dynamics software, we've made that far more efficient. So with the same compute power, you can do more cases. So we used to do, before restrictions came in, we used to do 350 runs in the wind tunnel per week. So that's 350 of your ideas being tried in the wind tunnel every week. And probably 500 or 600 CFD cases at Sauber, who had the biggest supercomputer. A typical Formula One team now, with far fewer resources, will do better quality CFD results, and they'll do 2,000 ideas every week using the CFD computers. So that's one contribution in terms of understanding aerodynamics. And then the other contribution that Formula One teams have made is doing correlation work between the track, the wind tunnel, and CFD, and dramatically improving the correlation between the simulations and reality.
Big data.
Eh?
Big data.
Big data. Well, yeah, huge data, and understanding that huge data. And this is
What
where,
you
for
do,
example,
right?
for example, the work we did at Southampton with Professor Zhang's students, understanding the fundamentals. That's another contribution that the Formula One teams have made. And the teams are now actually restricted. They're allowed to continue to do fundamental research, but they're not allowed to do research on a Formula One model. And actually, the fundamentals, it turns out, teach you more, actually, than doing Formula One development with students. Very good question.
Perhaps my question may not be directly relevant to the design, but majority of the time actually spent around the corner instead of speeding in a very straight lane, and where the driver's role becomes more important. and what do you do to improve the cornering of the car to win the game, win the race?
Yep. So aerodynamic downforce is what you do to improve the. So a Formula One car weighs, nowadays it's 700 kilo. They're fat because of safety reasons and because of the powertrains and batteries. They're fat. But that's half the weight of a normal road car, or less than half the weight of a normal road car. and we will generate in medium speed corners 2 tons of downforce. So the car weighs a bit more than half a ton. We're generating 2 tons to push the wheels, and that's why it's fast around the corners. And it is around the corners that a Formula One car, actually, that's where it's fast. Around the corners, in the braking zone, that's where a Formula One car is fast. And the drivers are also part, you can imagine a Formula One team, Mercedes have 700 plus people on the chassis side and more than 500 people on the powertrain side developing the car. When you have so many people, there is always going to be one brain somewhere thinking about what's the next thing we can do. So we include the driver training, driver psychology, so physical training, psychology, what he's doing with his mind, what he's doing with his eyes, where he's looking, how far ahead is he looking. The teams will look at anything they can. Really, I mean, I could talk for, you can probably all realize, I could talk for a week, easy.
Is the toe in or toe out fixed in a car or can dynamically change? You know,
Sorry?
the tire. You can toe in or toe out, you know, in the cornering. Yeah.
Right, okay.
Can it change within a race? Dancing. Okay. Yeah.
It's not allowed. So we have to have passive suspension systems, but we've tried everything you can. So we've tried, for example, having active rear wheel steer in the past, but that's now banned. We have, so a normal car would have Ackerman. A Formula One car will tend to have changing Ackerman to anti-Ackerman depending upon the steer. They'll play every game that they can. It has to be fixed once the race starts. But you'll have a different amount of Ackerman for Monaco that you'll have to other events because you've got really tight hairpins. And for example, the cars will run a huge amount of, word escapes me, caster. So we start with a reasonably high negative camber, and as you turn the wheels, you'll get quite high negative camber on the outside wheel and almost zero on the inside wheel. And that's all about trying to maximize the mechanical grip as well. Now, actually, in the past, teams have compromised the mechanical grip for aerodynamics because aerodynamics was so powerful. But you need both. It's clear you need both.
Lucky we don't have Formula One insider here in the audience. We have to finish with youngsters' question. But before we do, I have for students in the audience, tomorrow there's more trade secret at 4 o'clock. There's another lecture by William, and he will tell you what really happens. Okay, very valuable opportunity. So we have some students especially fly in from mainland to ask you a question.
I heard about data that there would be a 5-second gaining on the 2017 regulations. So I'm quite curious, is that possible, and on which specific circuit, because time changes from Monaco to Monza. Yeah, thank you.
So what next year, the rules change from the perspective of aerodynamics, and they also change from the perspective of the tyres that go to wider tyres. And so there have been stories that the cars will go 5 seconds a lap faster. Now, I think there will be variation. Pat Simmons from Williams have come out and said, well, my people, I don't know why he's done that. Pat Simmons is the technical director of Williams, and he's come out and he said, we aren't as good as innovating as other teams. Is he a motivator? I don't understand. If someone says to me, you're no good, what do? Do you work harder? Me, I don't. If someone says to me, you're no good, I go home. Yeah? Because I give everything already. Yeah? So different human beings are motivated in different ways, but it strikes me as really strange that a team boss will say, my people are no good, because we're not good. Yeah? That's not smart. But so there are some teams starting to say, we won't find 5 seconds. Yeah? But for example, in 2009, when Braun already in the early months of 2008 knew that their 2009 car would be faster than their previous car, not slower, just on aerodynamics alone, there'll be a big variation. When the rules change, and this is a big rule change, The rule change is the front wing, all bodywork becomes wider, the overall car becomes wider, so you get more floor area to work with. The front wing becomes wider, it gets pushed forward into a delta. The rear wing gets pushed back on a sort of delta in side view, and because the rear wing's pushed back, a little bit of the low pressure from the back of the rear wing can work onto the floor gets more expansion, the cars will be much faster.
Okay, William.
I think the big gain in lap time is going to be in medium speed tracks.
To be continued tomorrow at 4 o'clock.
What, run out of time?
Yeah, around the top time. But tomorrow there are more trade secret for youngsters. So tomorrow 4 o'clock, do turn up. Okay, thank you very much, William.